it is time to talk about derivatives of trig functions. So I'm not going to actually prove that the derivative of the trig functions are what I'm about to tell you, but they are very interesting to look at. They do require some trig identities that you might be a little rusty on. So I'm going to concentrate instead on how to use the derivatives. So today I want to talk about simple harmonic motion. So this is something you might study in a physics class. First year physics class, actually. It's a really cool idea, and it's described here in this paragraph, so I'm going to read it to you. Simple harmonic motion models the motion of an object or weight bobbing freely up and down on the end of a spring. So you can see a picture here where the spring is going up and down with this weight on it. Now this is with no resistance. If you want to do resistance, you take physics class, have fun. We're just going to do the very simple basic case. The motion is periodic and repeats indefinitely. So we represent it using trigonometric functions, because a trig function, it repeats every 2 pi, or depends on the period of the function, but here we're going to talk about sine and cosine. They have a period of 2 pi. So this, what does that mean that this repeats indefinitely? So this object is going to go up and down and up and down. And it's not going to stop. That's what it means indefinitely. It's going to do the same motion over and over and over again. So kind of like you've seen those little balls where you pull one ball back and you let it go and it hits all the others and it pops one and yeah, it goes back and forth. It just keeps going and going and going. That's kind of the same idea here, but it's on a spring. Where am I? The next example models motion with no opposing forces. So there's no friction involved in this example we're going to do. All right, so example. Oh, let me go back and talk about the derivatives. We didn't do that. So in order to do this problem, we're going to need to have the derivative of sine or the derivative of cosine. We're going to have to study and understand why we're using the function that we're using in our example. All right, so just a rule, derivative of sine is going to be cosine. Why? There's a proof of it. You feel free to go look at it. It's really cool. But I'm just going to concentrate on how to use the derivative. The derivative of cosine is negative sine. You have to get that right. The derivative of cosine is the one that always has the negative on it. You're going to have a couple more trig rules in the next video, but for now, let's just use those two. So simple harmonic motion. Example, a weight hanging from a spring, you can see the picture there, is stretched down 5 units beyond its rest position. So if I were to just let the weight just set in place, and not like pull it down or throw it up or anything like that or push it up. If I were to just let the weight hang at its natural position, non-moving, it would be in this middle position here. So it says it's stretched down, so they pulled it down. So they're stretching the spring down 5 units beyond its rest position, and then they released it. Now notice they've marked this at t equals 0. So this is our initial time. Now they release it to bob up and down. So it goes up and down and up and down. So this isn't 3 springs. This is the 3 positions of the 1 spring. Its position at any later time, t, is this position. So s is still representing our position function, which is good. So we understand what that is. And it's 5 times cosine of t. So they're using the cosine function to represent where this spring is, or this weight is at over time. So for example, at t equals 0, we plug 0 in, we get cosine of 0 is 1. So s is equal to 5 times 1, or 5. So that's why they've chosen this particular function, is because when t equals 0, it's at 5. If you had a different way of writing how far or your position, it might be a sine function that works better. If we call this position height of 0 and then 5 and then 10, then we would use probably the sine function in that case. But this is better for cosine. What are its velocity and acceleration at time t? Well, if this is a position function with respect to time, how do we find the velocity and acceleration? You remember? If you know, you can go ahead and try it. You have the derivative rules for this case. We need cosine right here. Derivative of cosine is negative sine. So you can go ahead and try these and come back and finish the video. All right, if you got it, then let's see if you can tell me what to do. How do you find the velocity? The velocity is the first derivative of position. Now, in order to find the derivative of this, you need to understand that 5 is a constant multiple. So he just hangs out, chills out, while we take the derivative of cosine. The derivative of cosine is just a rule that we have to memorize, minus sine of t. Make sure you use the right variable. Now, notice I put parentheses here because I don't want this to be misinterpreted as a subtraction. This is 5 times a negative sign. So finish it, work it out. Negative times a positive 5 would be a negative 5 sine of t. And that's your velocity function. What would be your acceleration? How do we find acceleration? Remember, that's the second derivative of position, or the first derivative of velocity, which is what we have here. So we just need to take the derivative of the velocity function. So negative 5 times, because that's the constant multiple, he just chills out. The derivative of sine is cosine. In this case, there's not really any simplifying, so I could just erase my, well, that didn't work very well. I could just erase my multiplication and leave it, but my eraser's too big, so I'm just going to write it nice and neat, and there's my acceleration. All right? So in this case, it didn't give us an actual time that they were interested in, but if we want a particular time, we want the velocity and acceleration at that particular time, we'd plug it into each of these functions and find out what the velocity and acceleration were at those times. So this is just a cool example.